The Southwest Iberian margin, a region straddling the boundary between the African and Eurasian tectonic plates, is a hotspot of geological intrigue and seismic activity. But here's where it gets controversial. Despite decades of research, the exact mechanisms driving some of the largest earthquakes in Europe here remain elusive. This area experiences a slow but steady oblique convergence at about 4 millimeters per year, where the African plate nudges against the Eurasian plate in a west-northwest to east-southeast direction. This tectonic dance creates a complex network of faults on the seafloor, including strike-slip faults running WNW to east-est and thrust faults oriented NE southwest. These faults are responsible for uplifting underwater mountains, or seamounts, which act as natural dividers between deep ocean plains known as abyssal plains. Historically, the Southwest Iberian margin has been the source of some of Europe's most devastating earthquakes. The infamous Great Lisbon Earthquake of 1755, with a magnitude estimated between 8.5 and 8.7, unleashed catastrophic ground shaking, tsunamis, and fires that devastated Portugal and claimed tens of thousands of lives. Other significant seismic events include the 1356 and 1761 earthquakes, both ranging from magnitude 7.5 to 8.5, and the more recent 1969 earthquake, which registered a magnitude of 7.9 and occurred roughly 200 kilometers. These features frame the Horseshoe Abyssal Plain, a flat oceanic basin that has been the stage for some of the Atlantic's most significant historical and recorded earthquakes. While the exact epicenters of older quakes remain uncertain, modern instrumental data provide approximate locations, though with some uncertainty. The West Iberian margin exemplifies a hyperextended magma-poor continental margin, where the continental and oceanic crusts are separated by a zone of exposed serpentinized mantle rock. This serpentinization, a process where mantle peridotite reacts with water to form serpentine minerals, weakens the lithosphere and influences tectonic behavior. Seismic anomalies detected beneath the Horseshoe Abyssal Plain, shown in darker green on seismic maps, hint at complex subsurface structures. These data were compiled using advanced geospatial software and seismicity records from global databases. Despite the historical significance of the 1356, 1755, and 1761 earthquakes, their offshore locations and occurrence before modern instrumentation make them poorly understood. The 1969 earthquake, however, was recorded instrumentally and intriguingly occurred about 30 kilometers beneath the flat Horseshoe Abyssal Plain, away from known major faults. Initial interpretations suggested it originated on a north-dipping thrust fault deep in the lithosphere, possibly a large trans-lithospheric thrust responsible for consuming oceanic lithosphere. Yet, high-resolution bathymetric and seismic reflection surveys have failed to detect such a major north-dipping fault at shallower crustal levels. Instead, mapped faults tend to dip southward, such as the Gorringe Northern Thrust, which uplifts the Gorringe Bank seamount by about 5 kilometers. This raises a critical question. What tectonic mechanism could produce such a deep, large-magnitude thrust earthquake beneath a flat abyssal plain covered by undisturbed sediments? Over the past half-century, numerous seismic and multi-beam surveys have sought the elusive sources of these great earthquakes, often focusing on prominent features like the Gorringe Bank. However, large portions of the Horseshoe Abyssal Plain remain underexplored. One seismic refraction profile crossing this plain revealed a step in the lithosphere interpreted as a blind, south-dipping thrust fault, but its proximity to a major strike-slip fault complicates this interpretation. Various conceptual models have been proposed to explain the region's high seismicity, yet no consensus has emerged. Here's the exciting twist. By integrating recent seismic and geological data with new numerical models, researchers propose a groundbreaking geodynamic interpretation. High-resolution teleseismic P-wave tomography, enhanced by ocean-bottom seismometer data, confirms a high-velocity anomaly beneath the Horseshoe Abyssal Plain extending down to 250 kilometers depth. Some have suggested this anomaly represents a nascent subducting slab, signaling the initiation of subduction. However, this would imply over 200 kilometers of crustal shortening offshore Southwest Iberia, which contradicts geological reconstructions showing only 20 to 50 kilometers of shortening at crustal levels. This discrepancy suggests the presence of decoupling layers within the lithosphere, allowing different deformation amounts between deep and shallow levels. Detailed seismic studies reveal a cluster of earthquakes at depths between 20 and 60 kilometers within the lithospheric mantle beneath the Horseshoe Abyssal Plain. The scarcity of earthquakes above 20 kilometers supports the idea of mechanical decoupling between the unserpentinized lithospheric mantle and an overlying serpentinized mantle layer and crust. Seismic refraction data further show that the basaltic oceanic crust is absent beneath the Horseshoe Abyssal Plain, with sediments resting directly atop serpentinized mantle rocks. This contrasts with the African domain south of the plate boundary, which features a thin basaltic oceanic crust. This structure results from the West Iberian margin's history as a hyperextended, magma-poor rifted margin, where mantle rocks were exposed during early seafloor spreading without forming a typical basaltic crust. Serpentinization is not limited to this margin. It also extends along oceanic transform faults and fracture zones, as evidenced by studies in the equatorial Atlantic. This widespread serpentinization creates mechanically weak zones that can decouple the crust from the underlying mantle. So, what mechanism could explain these observations? The answer may lie in a process akin to delamination, or peeling of the oceanic lithospheric mantle, a phenomenon well documented beneath continental mountain belts and collision zones, but rarely observed in oceanic settings. In this scenario, plate convergence triggers the detachment and sinking of a lithospheric mantle block, facilitated by the weak serpentinized layer that separates the buoyant sedimentary crust from the denser lithospheric mantle below. The presence of two bounding weak zones, the Gloria Fault and the Tiedemann Fracture Zone, allows this block to delaminate and sink downward. This process reconciles the limited crustal shortening with the deep seismic anomaly and explains the sagging of the Horseshoe Abyssal Plain and its thick sedimentary fill. To test this hypothesis, researchers employed two-dimensional numerical simulations using the Underworld Code. These models simulate the interaction of two oceanic plates representing Africa and Eurasia, incorporating a serpentinized layer on the Eurasian side and imposing a convergence velocity of 8 millimeters per year, reflecting faster Cenozoic plate motions. The models explored scenarios with one or two vertical weak zones, mimicking the Gloria and Tiedemann faults. The results are striking. In models with a single weak zone, the thinner Eurasian plate subducts beneath Africa, creating a subduction channel and accommodating about 200 kilometers of crustal displacement, contradicting geological evidence. However, when two weak zones are present, the block between them sinks northward beneath Eurasia, thickening the serpentinized layer and decoupling deep lithospheric deformation from the crust. A new north-dipping fault forms at the boundary between the detaching mantle block and the overlying crust, while a south-dipping thrust fault develops in the sedimentary cover, resembling the Gorringe thrust. This configuration matches seismic observations, including the location and depth of the 1969 earthquake. Further tests showed that once initiated, the sinking of the lithospheric block continues even if convergence stops, indicating a gravity-driven component. Importantly, delamination only occurs in models featuring a sufficiently thick, serpentinized layer and two bounding weak zones, highlighting the critical role of these geological features. This model elegantly explains several key observations: the deep high-velocity seismic anomaly beneath the Horseshoe Abyssal Plain, the mechanical decoupling between crust and mantle, the presence of a blind north-dipping fault responsible for deep seismicity, and the formation of the south-dipping Gorringe thrust. Yet, the debate is far from settled. Alternative interpretations involving nascent subduction slabs remain plausible, though they struggle to reconcile the deep seismic features with limited crustal shortening. Moreover, the natural structure may be more complex, potentially involving three-dimensional geometries and multiple decoupling levels. Current seismic reflection data only penetrate about 10 kilometers deep, while the main seismogenic structures lie around 30 kilometers depth, underscoring the need for further high-resolution imaging. Drawing parallels with continental delamination, one might expect a thermal anomaly to develop about 10 million years after delamination begins. However, ongoing convergence in this region may close any lithospheric gaps, preventing hot asthenosphere from rising and masking thermal signatures. Gravity anomalies also support the delamination model, a positive Bouguer anomaly over the Gorringe Bank where serpentinized mantle protrudes, and a negative anomaly over the Horseshoe Abyssal Plain where the sinking block resides. Additionally, the thick Cenozoic sedimentary layer filling the Horseshoe Abyssal Plain suggests subsidence consistent with the downward pull of a delaminating lithospheric block. What does this mean for seismic hazard and geodynamics? Calculations based on the tomographic anomaly's size and the 1969 earthquake's focal mechanism suggest a fault capable of producing an earthquake as large as magnitude 8.6 if it ruptured fully, or magnitude 8 for a partial rupture matching the 1969 event. This insight potentially solves the long-standing mystery of where such large earthquakes originate offshore Southwest Iberia. The identification of oceanic lithosphere delamination here is groundbreaking, with profound implications. This process appears to be forced by plate convergence and facilitated by serpentinization and bounding fracture zones. Its rarity worldwide suggests it requires very specific conditions. Old, thick, serpentinized oceanic lithosphere with pre-existing weak zones and some degree of convergence. Such conditions are typical of hyper-extended magma pore margins and diffuse plate boundaries, making detection challenging. Could oceanic delamination have been more common in Earth's past? Possibly. During periods when older, unstable oceanic lithosphere was widespread, such as late stages of ocean basin cycles or the Archean Eon, this process might have played a larger role. Early Earth may have featured a thick, serpentinized crustal layer, facilitated by crustal fracturing from meteoritic impacts. Delamination could have been crucial in forming the first continental blocks before modern subduction zones developed. While oceanic delamination is not a dominant mechanism for recycling oceanic plates today, it may be vital in the early stages of subduction initiation. Starting subduction in Atlantic-type oceans is notoriously difficult because it requires fracturing and bending of the lithosphere, which is often precluded by the plate's strength and lack of sufficient forces. The Southwest Iberian margin presents a unique natural laboratory where ongoing oblique convergence. Compressive stresses from the nearby Gibraltar subduction system and a serpentinized lithosphere bounded by fracture zones create ideal conditions for delamination and potentially subduction initiation. This raises provocative questions. Could delamination be a necessary precursor to subduction? Does it require less mechanical energy than full subduction, making it a more feasible initial step? If so, might we be witnessing the birth of a new subduction zone in the Atlantic? These questions challenge traditional views and invite lively debate. The proposed evolutionary model envisions continued convergence, reactivating the Gloria and Tiedemann fracture zones, isolating a lithospheric block beneath the Horseshoe Abyssal Plain. This block begins to delaminate and sink northward, generating a major thrust fault responsible for deep seismicity, including the 1969 and possibly the 1755 earthquakes. If this process persists, the block will eventually be removed, allowing the Eurasian lithosphere to subduct beneath Africa, forming a new subduction interface. This nascent system may merge with the Gibraltar Arc and other subduction zones, potentially leading to the gradual consumption of the Atlantic Ocean. In summary, the Southwest Iberian margin offers compelling seismic and geodynamic evidence for oceanic plate delamination, a process that could reshape our understanding of plate tectonics and earthquake genesis, but this interpretation is not without controversy. Alternative models exist, and the complexity of the region demands further investigation. What do you think? Could oceanic delamination be the missing piece in explaining these massive earthquakes? Or is subduction initiation the more plausible scenario? Share your thoughts and join the conversation.